So, we just got done talking in the last chapter about how electrons are waves and particles at the same time, and it seemed all very mysterious and complicated. And then here we are with Lewis' theory, and we're making electrons to be nice little dots, right? This is oversimplifying the electrons. We talk about electrons being shared between two atoms. The electrons are not always shared equally. If you've ever shared a bed with someone, you know that some things can happen with the blankets, right? There's always somebody that tends to grab the blankets and the other person is literally left out in the cold. And there can be huge fights over that. So if we look at hydrogen and fluorine are sharing a pair of electrons. But that pair of electrons is not equally shared. So I have an analogy that I kind of like, because I think of electrons as being a lot like little boys. They remind me of my son Andrew. So if the electrons are like little boys, then the atoms are their homes or their families, right? So we have in this bond, let's just put the electrons there. 1 electron, 2 electrons. We got 2 electrons. So those are 2 little boys that went out to play. And hydrogen's home is pretty basic. They've got a black and white TV and a VHS recorder and some old Thomas the Tank Engine VHS tapes. If you're hungry, the mom will give you some bread and butter and a glass of water. They don't even have an ice cube maker. I mean, this is very basic over there. Over here at Florine's house, they've got the big screen TV, the satellite dish with all the channels, and they've got every game system known to man. They've got a pool and a trampoline and a soda fountain in the kitchen, right? So think about these 2 little boys. Where are they going to spend most of their time? They're going to go over and play at Florine's house. Why? It's more attractive, right? It attracts them. So fluorine has greater attraction for those electrons than hydrogen does. Now, this is not an ionic bond. An ionic bond would be hydrogen giving its electron to fluorine, and I suppose you could say that would be the hydrogen family putting their son up for adoption, maybe, and fluorine's going to take him in and adopt him. That's not what's going on here. So they're spending more time over here, and so if we look at the charge distribution around this molecule, we see that there's more negative charge around the fluorine atom than there is around the hydrogen atom. So we use this notation to indicate that the fluorine end of this molecule is partially negative. This squiggly thing here is a Greek lowercase delta. Kind of looks like a lowercase d with a posture problem. That means a partial charge. This isn't an ion with a -1 charge. That might be a -1/3 charge or a -1/16 charge or something. Exactly what it is, we don't care at this level. It's just a partial charge. And over here is a partial positive charge. So this end's positive, that end's negative. Here we have an illustration of hydrogen fluoride molecules. They are in the gas state at room temperature, and we've got 2 metal plates here. If we just leave them alone, they're just kind of randomly oriented in space. If we turn on the electricity and put a negative charge here and a positive charge here, the negative ends of the molecules will be attracted to the positive plate. The positive ends will be attracted to the negative plates, and they will all stand at attention. They'll all just line up because they are polar molecules. The ends are different. So our Earth is a sphere, right? But there's a North Pole and a South Pole. There's something different about that part versus exactly on the opposite side. So a polar covalent bond, we have shared electrons, but they're not shared equally. And so one end is different than the other. So these are they're going to fall into a continuum between ionic bonds and pure, or what I prefer is nonpolar bonds. This notation with the arrow, I think of that as, Dad's coming home and he wants to, ask his son how was school, and so there's a neighbor outside, and he asks the neighbor, "Where'd those boys go?" And the neighbor points. "They went over there," pointing to the fluorine house, because that's where they are. So the arrow points to the more electronegative, the more attractive to electrons, where the electrons are spending more time. And then at this end of the arrow, we make a plus sign. So this is the positive end, and that's the negative end. So there's two different ways to indicate the polarity of that bond. Any questions? So electronegativity is the ability of an atom to attract electrons to itself in a chemical bond. So fluorine has high electronegativity. It's very attractive to the electrons. I mean, I'd like to go over to fluorine's house. That sounds like a great place. Electronegativity is inversely related to atomic size. So a larger atom actually has lower electronegativity. A smaller atom has higher electronegativity. So let's look at this table here. So here we have fluorine. The height of these blocks represents electronegativity. 4.0 is the highest electronegativity, and that would be fluorine. And it's all literally downhill from there. We left the noble gases off here because they barely form any compounds at all, and so there's really no point in even talking about electronegativity for the noble gases, so we just leave them out. So as you go across a period, electronegativity increases, the atomic radius decreases. As you go down a group, the size increases, the electronegativity decreases. So that table has all these nice values in it, and there are calculations and questions and things that you can answer where you might need to look at those values. We won't have anything like that on an exam, because what you need to go on in chemistry is you just need to have the big idea, the qualitative, is it polar or not? Which is more electronegative? Which is less? We don't actually need to look at the numbers most of the time. So as you get closer to fluorine, more electronegative. There are some here like carbon and iodine have the same electronegativity. Nitrogen and chlorine have the same electronegativity. And so there are situations where that might be important, but most of the time it really just doesn't matter. So how polar is a bond? Some bonds are more polar than others, and how polar it is depends on the difference in electronegativity. So we can represent that as delta En. So the difference between the electronegativity of the one and the electronegativity of the other. So there's a continuum from 0 electronegativity difference up to 3.3, and that would be the largest electronegativity with the smallest. That's the biggest difference that there is. So this, of course, would be ionic, and this is pure covalent or nonpolar covalent, shared equally. And there's a continuum in between. So we set some arbitrary guidelines in there. I mean, it's a little bit like if you look at the people who live in the United States, and there's upper class and middle class and lower class. Well, where do those divisions come from? They're arbitrary, right? So these are arbitrary divisions. If the difference is 0.4 or less, we're going to call it a nonpolar bond. If the difference is 2.0 or larger, then it's an ionic bond. And if it's in the middle here, it's a covalent bond, but it's polar, meaning the electrons are not shared equally. So how do we identify what kind of a bond is present? So you can look at electronegativity differences and compare them here. That works. But what if you don't have the table of electronegativity values? So I'm going to show you just sort of the rules of thumb so that you can predict. So if you have two identical atoms, like two chlorine atoms or two hydrogen atoms, their electronegativities are the same, right? Because they're the same element. So this is going to be nonpolar. You're definitely going to have an ionic bond if you have a metal and one or more nonmetals. We learned that in chapter 3. We learned to name compounds, and we learned that if it's got a metal and a nonmetal in it, it's an ionic compound. We need to use this set of rules. If it's an ionic compound, it's got ionic bonds. In between is polar covalent. Two different nonmetals. Now this one is not always true. Like I pointed out in the previous slide, carbon and iodine have the same electronegativity, right? So that would be a nonpolar bond. Those sorts of situations don't come up very often. There's only one exception that you need to know. Carbon-hydrogen bond. That's nonpolar. And the reason it's nonpolar is the difference in electronegativity between carbon and hydrogen is only 0.4. So it's right on the edge, but it's a nonpolar bond. In OChem, there's carbon-hydrogen bonds everywhere, because that's kind of what defines compounds as being organic. And so I do want you to know that if you see carbon and hydrogen, that's a nonpolar bond. Otherwise, if you've got two different nonmetals, I expect you to tell me it's polar. Yeah?
So like the most acids is the polar or something?
The what acids?
The most acids. Like HF and like that.
Yeah, so HF is a molecular compound. HCl. Mm-hmm. So those are going to be polar covalent compounds, not ionic. If they're pure, they're going to be a gas at room temperature. When we dissolve them in water, they form ions, but they are not ionic compounds. They're polar covalent compounds. So, oh yeah, there's this one. The degree of bond polarity can be measured, and one measure of that is the dipole moment. And we're not going to do much with this, but it's something that you need to have heard about, right? And then if you need it later, you'll learn more about it later, but you just need to hear about it for now. So a dipole moment, abbreviated with a mu, that occurs whenever there's a separation of positive and negative charge. And the equation for dipole moment is Q times R. Q is the charge magnitude, R is the distance between the two charges. The common unit is the debye, which is 3.34 times 10 to the minus 29. Coulombs times meters. Coulomb is the charge unit, meter is a distance unit. So here's a table with 4 different molecules, and we're comparing difference in electronegativity with dipole moment. Dipole moment is something that would actually be measured, and delta En would be just calculated by looking at the chart. So for chlorine, we see that the difference in electronegativity is 0 and its dipole moment is 0. ClF, now we have a difference in electronegativity and we see a dipole moment. They don't match up exactly. HF, very polar molecule, 1.9 delta En. So if you go back to the continuum there, HF is just under being an ionic compound, but it's not ionic. Dipole moment 1.82. Lithium fluoride, is that ionic? Is lithium a metal?
Yes.
Lithium's a metal, it's ionic. Delta En is 3. The dipole moment's actually 6.3.
So we said if larger than 2 point, is that
Yeah. We generally say if delta En is 2.0 or larger, then it's an ionic bond. Another way to look at this is percent ionic character, where you take the bond's actual dipole moment divided by the dipole moment that would exist if the electron was transferred completely. So if it was a transfer. So of course the most you could get is 100%, the least would be 0. So here what we're doing is we're graphing percent ionic character versus electronegativity difference. And so there's a cluster of compounds down here. Their percent ionic character is very low, and their electronegativity differences are also very low. Here's HF, and he's very close to this cluster up here. All of these up here, except for HF, are a metal and a nonmetal. All of these guys are ionic. So we say that if the percent ionic character is 50% or greater, it's an ionic bond. And on the electronegativity difference scale, we said, well, if it's 2.0 or different, it's an ionic bond. So we see that HF doesn't quite meet either criteria. Some of these ionic compounds, though, actually have an electronegativity difference that's less than 2. So we talk a lot about ionic bonds as being an electron transferred from one to the other, and it's like bye-bye, see you, and they never get together again. No bond is actually 100% ionic. The electron is mostly transferred, but not completely. So there's a smidge of sharing going on, but mostly not. So that's the truth. And then we'll go back to the generalized lie that the electron is completely transferred. So we should be able to answer questions like this. Determine whether the bond formed between each pair is pure covalent. I don't want to use that word. Not that it's a bad word, but nonpolar covalent is more descriptive. Polar covalent or ionic. So here we've got iodine and iodine. So we mean nonpolar because we know that the electronegativities are the same, right? So this is a nonpolar covalent bond. How about cesium and bromine? Ionic, right? Because cesium is a metal, bromine is a nonmetal. Now, depending on what definition, I'm going to go back and look at this. Is cesium bromide on there? It isn't. Cesium iodide is on here. I can't do that. Anyway, there we go. Regardless of the other ways of identifying exactly what's ionic versus nonpolar or polar, if it's a metal and a nonmetal, I expect you to tell me it's an ionic bond. How about phosphorus and oxygen? Polar. So we have two nonmetals there, and they're not the same. So that's a polar covalent bond. Any questions?